All right, now we're going to switch gears a little bit and start to look at logic functions. All right, how we describe the operations we want to perform on our binary variables. All right. So just to draw a quick comparison, most of us are familiar, more familiar with looking at arithmetic functions. Arithmetic functions, take in some variables, n variables, and produce an output. Likely these variables are some element of real numbers, right? And so the domain is essentially n-dimensional real space, right? If you have n variables, you have n-dimensional real space as your domain, and the output is again some other real number. Okay, so it maps. We could say it maps r to the n to r. Right? Common representations would include you could write an equation, you could show a graph or a plot. Things like this to demonstrate or to visualize the representation. In a logic function, we also have n variables, but these are binary variables. Each one comes out of the set of 0, 1 only. And so our domain is a string of zeros and ones, and if we have n variables, we have n of these bits. Right? So we have an n-bit string, which means that there are exactly 2 to the n combinations. And that's it. A finite amount. Over here, because it's all real numbers, then there's an infinite number of combinations or number of input possibilities. Here we only have 2 to the n possibilities. So what a logic function does is it takes in one of these 2 to the n possibilities and it maps it to a single bit, to 0, 1. The output or the range of a logic function is a single value, 0 or 1. We can represent this again as a logic equation or as a truth table, or as a plot, which, again, since we can only take on the values 0, 1, we'll often call these plots waveforms, and you'll see why throughout the course, and others. So let's look at some of these representations. All right. Let's first of all focus on the domain. How would we visualize the domain of these logic functions? Well, we said there's always a finite amount. There are always 2 to the n possible combinations of our inputs. And so we could actually enumerate them all. And that's what a truth table does. It enumerates all the possibilities. Another way of looking at this is in n-dimensional space, right? Just like we were used to our arithmetic functions. What we could do is we could show each variable on an axis, so x, y, and z for 3 variables. If you had 2 variables, it would just be x and y. Right? But these variables can only take on the value of 0, 1, and so there's only 2 valid locations in each dimension, right? And so when you superimpose, or when you use all the dimensions for 3 variables, you would arrive at a cube. For 2 variables, you'd arrive at a square. For 1 variable, you'd arrive at a line segment, all right? And for 4 variables, you could start to draw what's called a hypercube. After 4 variables, it becomes very hard to draw these out, all right? So this is less commonly used, but we could visualize it as actually n-dimensional space. Another way is what we could call a binary tree or a binary decision tree. What these are is each level in our tree represents a single variable, and the junction indicates a split as to whether that variable is 0 or 1. So if I go this way, x is 0, this way, x is 1. Then I get down to the y level. All right. And again, if y is 0, I go this direction. If 1, that direction. And I split again. And then the z level. If z is 0, I go this direction. If z is 1, I go here. And you reach these terminal points, right? I've reached these different pathways. How many are there? Again, exactly 8. 1 for each combination. Over here, there are exactly 2 to the n vertices, or corners. Again, 1 for each combination. So these are just different ways of visualizing the different combinations you have. All right. A last one that's common, maybe a helpful way to visualize things at first, are Venn diagrams. If you've never seen Venn diagrams before, it's a set of interconnected circles. Let me go through these. Each circle represents a variable, and the area inside the circle represents where the variable is true. Outside is where the variable is false. All right? And in a Venn diagram, you shade or color in the regions where the function is true. So if I give you the simplest logic function, f is equal to x, then what I'm saying is f is true when x is true. If I gave you the function f equal to x naught, or x prime, or x bar, sometimes you'll see it x bar. This just is really not x, right? So here's f, here's x. When will f be true? F will be true when x is 0, right? So for all the area outside of x, which is where x is 0, f is true. If you have two variables, you would draw your Venn diagram like this and take very careful notice. With two variables, we should make 2 squared or 4 combinations. Notice there are exactly 4 distinct regions, right? This region is inside x but outside y. And so this is where x is 1 and y is 0. This is where x and 1 and y are both 1. It's where they intersect, and so on. All right, so each region represents a separate combination. You could show actual functions, so if I said x or y, right, look at that function. Then the Venn diagram would shade all the areas where x is true or y is true. That's all of this shaded region here. If I give you the function x and y, it's only true where x and y are both true. That is the intersection of them. All right. As we go throughout the course, we'll be able to actually perform operations. So if I give you some small function, let's say x bar, you would produce, it's the shaded region where x is false. Some other function, so let's say, here's g equal to x bar, h is equal to y. What if I say, tell me what g and h is? I want you to and these two functions together, these two Venn diagrams together. Well, when you and Venn diagrams, you take what's called the intersection. You take where they're both shaded. An easy way to visualize that is the old yellow and blue make green principle, just like your Ziploc baggies. When you squeeze it together, yellow and blue make green, all right? And so imagine you layered this on top of this blue Venn diagram here. Where would you see green? Wherever you see green, that's the answer. That's what you shade in. And so x bar and y is all the area where that's outside of x and inside y. All right? If you take the or of the two Venn diagrams, wherever any region is shaded, you shade in the resulting Venn diagram. Right? So you take the union of those.